Hello and welcome to my talk. I am Rahul Gopnath and I work at CISPA Helmholtz Center for Information Security at Saarbrücken, Germany. This talk is based on our research abstracting failure-inducing inputs. Our work has received Distinguished Paper Award at ISSTA'20. Often during fuzzing, when we feed a program with a large input, it fails. And quite often, the input is extremely large and difficult to debug. So the question is, why did my program fail? What is the smallest input that can reproduce a failure? What are the specific circumstances under which my program fails? And for this talk, let us say our predicate behaves like this pattern matching. That is, the program fails if there is a nested parenthesis. The traditional technique for input reduction is an algorithm called delta debugging. That is, we start with a failure-inducing input and then split that input into smaller and smaller fragments. Each of these fragments are then passed through the program. And we check to see whether these fragments can be removed without removing the ability to reproduce a failure. And the smallest input that can reproduce a failure is then returned to the user as the minimized string. Unfortunately, traditional delta debugging fails when it is faced with structured inputs, such as inputs to an interpreter. The problem is that the interpreter expects every input to the program to be syntactically valid. Since traditional delta debugging is not structure aware, it fails in identifying fragments that can be removed without causing a syntactical failure. That is, we have to use techniques that can generate inputs without syntax error. And these techniques, they exist and they are collectively called hierarchical delta debugging techniques. And these techniques first use a context-free grammar to parse the input into a parse tree. So here is our parse tree. The idea is to start scanning from the root node and then look for smaller subtrees that replace the current node, here start, and then reproduce a failure. So since we start at the start node and there are no more start nodes in the tree, we go to the next node. So here we move to the expr node. And we scan for the next expr node and check whether this new expr node that is smaller than the previous can actually replace the previous node. And the generated input, that is double nested 1 times 3 by 4, can reproduce a failure. So we replace the previous tree with a smaller tree and then continue. And we come to the term. So can we replace this term with any of the smaller terms? So replacing this term with a smaller term, we generate an input which is a nested 1 times 3 by 4, and that does not reproduce the failure. So we continue looking and check whether we can actually reproduce this. And again, 1 times 3 by 4 does not reproduce a failure. Similarly, we continue and then we come to the next term. And we check whether we can reproduce a failure by replacing the previous term with this term. And the tree thus produced is double nested 3 by 4, and that actually reproduces this failure. So we can continue with the new tree. And this tree again can be reduced by looking at the next term. And we get double nested 4, which reproduces the failure. And since there are no more nodes that can be replaced, the recursion ends and we return the current expression. That is, we can reduce the much larger expression into a smaller expression that can reproduce the same failure. However, this minimized string leaves a number of questions unanswered. Before prioritizing a fix, a developer might need to know a number of things about the behavior of this particular fault. For example, they may want to know if the failure is caused due to the minimal string. That is the size 5 characters anyway important to the failure? Or is the failure due to the presence of number 4? Or is it because of the double parenthesis? For example, can the failure be reproduced if we simply have 2 paired parentheses rather than a nested parenthesis? Or does it have something to do with the fact that the negative sign is not used? Can we use any number instead of 4? What about any other variable? So none of these questions are actually answered by this minimized string. And we actually looked at a number of fors and their minimized strings in a number of different projects. So the developers need to know the answers to many of these questions before forming an initial judgment on what part of the program was involved in the failure. And here are a number of these kinds of faults from real-world projects. None of these minimized strings are actually informative, and in many cases, the initial idea that is formed from a casual inspection is often incorrect. So the question is, can we do better? So here is the input string. Can we do better? So our technique, which is called DDSET, can identify which parts of the input are actually causative and which parts of the input is just a failure. And it can do that with high degree of accuracy and precision. And here is how DDSET works. As before, we start with a context-free grammar for the input, and then we generate the parse tree. We start with the root node, that is the start here. And we use the context-free grammar to replace the node that we are looking at with a randomly generated node of the same kind. So here another tree that starts with start. And we try to generate semantically valid inputs. If we are not able to generate a semantically valid input, we ignore the currently generated input and then try again. So if any such semantically valid nodes are unable to reproduce the failure, then we mark the node as concrete and then continue. In this case, we generate a tree 1 times 2 minus 3. And that does not actually reproduce the failure. So we mark the start node as concrete and we continue. We come to expr and we follow the same procedure of random generation of valid nodes. Here we reproduced 1 times 3 plus 1 plus 3 plus 4, and that needs to be attached to the start. And the tree generated does not reproduce the failure. So expr is again concrete. And we move to the next term, that is term, and do the same procedure, 3 times 4, and attach it to the tree at the same part. And the generated string again does not reproduce the failure. And we do the same thing for the rest of the nodes, one at a time, until we come to the term expression, the last expression node, and we generate another expression that is 1 minus 2 and then attach it to the tree. The string that is actually produced by attaching to a tree is 1 minus 2 double nested, and that can actually reproduce the failure. But it could be a fluke because we are randomly generating these strings. What if we reproduce another string? That also reproduces the failure, and another, and another. And at some point we decide that we have seen statistically, we have seen enough strings that generates that reproduces a failure to have statistical confidence in the fact that this particular expression can be any random node of the same kind. And once we know that, we mark that expression as abstract and then prune the tree. And we extract our abstract failure-inducing input. And if you see this particular pattern, abstract failure-inducing input, it precisely answers all the questions that he had about the failure-inducing input. It tells us that it is a double-nested parenthesis, double-nested expression, where that particular expression can be replaced by any other kind of expression. This is a pretty reasonable aid for debugging, and it can help programmers to prioritize their inputs to say something that is related to exp. However, this is not the only use for it. However, this is not the only use for it. We can also use this expression as a generator for almost an infinite number of faults. So this is a pretty reasonable way of generating faults. However, there is one more wrinkle that we need to fix here. Consider this particular reassignment, so this particular predicate. The idea is that if there is a reassignment on a previously assigned variable with the same variable, then it causes an error. And it contains 3 parts. And the problem here is that if we replace the first v with a random node, it will not generate an error. And if you replace the second v with a random node, it will also not generate an error, and so for the third v. The issue is that all the 3 nodes need to be varying together in order for it to reproduce failure. And it doesn't really matter what variable it is. The only constraint is that the same variable, the variable name has to be the same. So what we do is that we scan the tree looking for concrete strings that match and of the same kind, here alpha, and then vary them together. And if all the strings that we produce that way also generate an error, then we mark them as sharing, and that is the generated expression. For example, here is an issue from the Rhino JavaScript interpreter. Constant square bracket y comma y is a square bracket, an empty square bracket. And you can see that this actually contains such kind of patterns. And we can actually successfully generate the abstract patterns from even these kinds of inputs. And of course, the DDSET algorithm works really well on the real world faults that we inspected. These were the examples that we looked at earlier, and these are the abstract patterns that we generated out of these bugs. So we also looked at a much larger set of real faults to make sure that DDSET actually works well in real world. So we looked at 3 different languages and 4 different compilers and Unix utilities. And for each of these projects, we extracted the abstraction for each of these faults. And these were the results. So the first column, program, and the second column is non-terminals that shows how many non-terminals we were able to extract from the fault. And the third column is variables, that's a sharing variables, that says how many of these variables were repeated. For example, the first one is 3 plus 2 is 5, which means that there was a variable v, there was a variable that was repeated 3 times. And there was another variable that was repeated 2 times. So in total, 5 positions. So as we can see, DDSET is actually able to abstract almost all of these faults. So this is actually pretty useful for the developer. What about DDSET as the pattern produced by DDSET as a producer? Here again, the first column is program. Second column is the number of valid inputs that were generated from the abstract failure-inducing pattern. So when we say that 62% valid inputs were generated, the rest of them were semantically invalid. They are syntactically valid, but semantically invalid. And in those cases, we generate more. And the third column shows the percentage failure. That is how many of these were actually able to reproduce the failure. And we see that almost all of them are able to reproduce the failures. So as you can see here, we have a high accuracy in producing semantically valid inputs that induce failure. A replication package for our project is available at GitHub. Further, we also provide a Jupyter notebook that explains all our techniques. So in summary, we have shown how delta debugging and hierarchical delta debugging works, and we have examined what are the deficiencies in these two algorithms. We have also looked at DDSET, how DDSET abstracts its input and how it is able to extract an abstract pattern that can be used by the developer not only as a debugging aid, but also as a generator for an almost infinite number of inputs, all of which can induce a failure or even other kinds of behaviors. We have also examined how DDSET, the abstract pattern that is extracted from DDSET, can actually handle even covariant inputs such as variables. Thank you for listening to my talk, and I'll be happy to take questions.